Is my screen visible? Is my screen visible? Hello, is my screen visible?
Yes, Dada.
Okay. So, so is a subspace spanned by they are denoting W by the sum of the subspaces. Okay. These things are obvious, na? Alpha has unique representation with respect to independent subspaces, because if alpha is in the sum, in this sum, and alpha has two representatives, two representations, one is summation alpha I, another is summation beta I, then you can see that this is 0 and hence these individual terms are 0. Okay. So these are some immediate observations. Now, what does this lemma tell us? V be a finite dimensional vector space. Let W1 to Wk be subspaces of V and let W equals to this. The following are equivalent. W1 to Wk are independent, and intersection of Wj with the rest is 0. And if beta I is a basis of Wi, then the sequence beta from beta 1 to beta k is an ordered basis for W. Okay, let's see. So first we assume that they are independent. Alpha be a vector in the intersection. Then there exist vectors alpha 1 to alpha j minus 1 with alpha in Wi such that this alpha 1 to alpha j minus 1 is equal to alpha, and you get this, right? Remember, since alpha is in the intersection, alpha belongs to Wj as well. But we know that this sum is 0 implies the individual vectors are 0, right? So alpha j equals to alpha is 0. Thus we get that this intersection is 0. Now, suppose you observe B and try to, what is B? B is this, intersection is 0 and you will have to conclude about the basis. Now, let us observe that B implies A. Suppose this. Now, let us observe that B implies A. Suppose this. Alpha I is in alpha I. Oh, let's observe that B implies A. Okay. So, suppose this is the sum. Okay. And let j be the largest integer I such that alpha I not equals to 0. See, it doesn't have to be the way that each alpha is non-zero. Na? There might be some I, for some I alpha I might be 0. They are taking the largest I. Call it j. So this is what they get. Then alpha j is minus this. Again you see this is in the intersection, na? Because the left hand side is in wj and the right hand side is in the rest. Like the right hand side is in the w1 plus up to wk minus 1, right? but this is 0. So you get alpha j is 0. And by this way, you can show that now alpha j is 0, but which is a contradiction because alpha j was supposed to be known the largest type for which alpha is not 0. So alpha j in particular is not 0, but here you get alpha j is 0. So here we are equivalent. Now they will show that A is equivalent to C. Let us see why A is equivalent to C. Let beta is a basis of Wi and let beta is equal to beta 1 to beta k. The span is clear, na? Because span is clear, na? W is this, so the bases are correspondingly beta 1 to beta k. So the union of these bases of course spans W. Only thing we check is that these are independent. Some linear combination of vectors beta I, since W1 Wk are independent, each beta I is 0 and so on. Okay. If any and hence all of the conditions of the last lemma hold, we say that the sum W1 to Wk is direct, or W is the direct sum of this, denoted by this. This is the notation of direct sum. Okay. In the literature, the reader may find this direct sum referred to as an independent sum or the interior direct sum of W1 to Wk. Okay, I will give you 3 to 4 minutes to go through these examples. These are pretty easy examples. You should be able to go through this. 5 minutes you take. These are not very tricky things. Okay, so just have a look at this. 5 minutes you have. Take your time. Theory we are going thoroughly. That's why I am directly presenting the book, because if I write down each and every expression, it will take a lot of time. Okay, so let's see what is there next. Let V is a vector space. A projection of V is a linear operator E on V such that E square is E. In general, if you think about, suppose there is a continuous map, okay, from X to A, where A is a subset of X, okay. So when we think about a projection, so then what we mean is that if square of f is f, I mean if compose f is f, okay. This is the, I mean, basic definition of a projection for any projection, huh? Okay. The vector beta is in the range of R if and only if E beta equals to beta. If beta equals to E alpha, then E beta is E square alpha, and E square is E, so E alpha is beta. Okay. Conversely, if beta is E beta, then of course beta is in the range. So you can see that the vector beta is in the range R. I mean range of E is R, then E beta is beta. That is, it is identity on the range. V is R direct sum n, where n is the nullity. Okay. So why is this? So suppose E is a linear transformation from V to V such that E square is E. Okay. So R is range E. R is range E, and N is kernel E. Okay. So for any V belongs to capital V, you can write this as like EV plus V minus EV, right? Observe that this thing is in the range, okay, and this is in the kernel. Why? Because if you apply V on this vector, E on this vector, you get EV minus E square V. But E square is E na, so this is okay. And you can also show that if a vector alpha is in both R and N, then it will become 0, because if alpha is in R, then there exists beta belongs to V such that E beta is alpha. Again, alpha is in the kernel, so E alpha is 0. Now E alpha is E square beta is 0, but E square beta is E beta na? Is 0, but this is again alpha, so alpha is 0. Thus this is a, so V is direct sum V is a direct sum decomposition of R and N. Remember this terminology. R and N subspecies of the, there is one and only one projection operator E which has range R and null space N. The operator is called the projection on R along N. Okay. Any projection E is trivially diagonalizable. Any projection E is trivially diagonalizable. I think we have done it now. That if E square is E, that implies E square minus E is 0. It means E satisfies x into x minus 1, this equation. So the minimal polynomial of E is either x or x minus 1 or x into x minus 1. In all the cases, they are product of distinct linear factors. So E is diagonalizable. Okay. So E has this block matrix form with respect to the basis of the kernel and union with the basis of the range, so on. Projection can be used to describe direct sum decomposition of the vector space. For suppose V is this, for each j we shall define the projection Ej on V such that alpha to alpha 1 take alpha k with alpha I belongs to I. Ej of alpha is j. So they are sending alpha to the jth component. Okay. Clearly Ej square is Ej, and also you can see the null spaces. Like the null spaces. What is n Ej? This is nothing but W1 direct sum Wj minus 1 direct sum Wj plus 1 direct sum Wk.
ভাই ইটা কি করে ডায়াগোনালাইজেবল হচ্ছে একটু বলবে? ইটা ডায়াগোনালাইজেবল কি করে হচ্ছে?
Do you remember the result that wait a minute. Do you remember this result? Read it. Okay. This was the result. This is what we used here. See, E square is E, right? So E square minus E is 0. It means E satisfies this equation, right? E satisfies this equation now. So minimal polynomial of x, we know that minimal polynomial of x should divide any polynomial which annihilates E, right? So what are the possibilities? X, x minus 1 or x into x minus 1? But you see all of them are distinct linear factors, product of distinct linear factors, okay?
আচ্ছা আচ্ছা আচ্ছা, বুঝতে পেরেছি।
Convince yourself the projection. Okay. So suppose V is W1 direct sum Wk, then there exist k linear operators E1 to Ek on V such that each Ei is a projection Ei square equals to Ei. Okay. And Ei Ej is 0 if I not equal to j. I is summation e1 to ek, and the range of ei is wi. So they are saying if v is a direct sum of k linear subspaces of itself, then there exists k projection which satisfy all this. Conversely, if e1 to ek are k linear operators on v, then each which satisfy these conditions, and if we let wi is the range of ei, then we get this decomposition of v. Okay. Proof. See, the proof is not very tough because the proof is not very tough. Why? We only have to prove the converse statement. So what about the other statement? So first of all, they are taking. So suppose given V is W1 direct sum WK. Okay. They are defining EI of alpha, where alpha is alpha 1 to alpha k, alpha I is in Wi. They are defining EI alpha to be alpha I. Okay. So clearly you can see that range EI is Wi, right? And also you can see that alpha is E1 alpha up to EK alpha, right? Because EI alpha is nothing but alpha I, right? Thus you get I equals to, I should write this. This is E1 up to EK of alpha. Thus you get I equals to E1 up to EK. Okay. Okay. Then yeah. And what about summation EI EJ? Okay. So suppose EI EJ of alpha. So what is EI of EJ alpha? That is nothing but alpha j, right? Where alpha is W alpha 1 to alpha k. But what is EI alpha j? What is that? Do you remember what is kernel of EI? That is this, as I wrote it down. Right? So this alpha j is in the kernel, na? Because alpha j is in alpha a. I not equal to j I should write. This is 0. So EI EJ is 0. So the upper part of the theorem is proved, that there exists k linear operator which satisfy all four. Okay. So this is done. We are talking about the converse, that if there are such linear transformations E1 to EK which satisfy 1, 2 and 3, 1, 2 and 3 means this and this, then V is a direct sum of V is a direct sum of the range. Okay. So first of all, if you take alpha belongs to V, then I alpha is, put the value of I here, which is E1 to EK of alpha, right? Which is E1 alpha. So alpha is E1 alpha up to EK alpha, right? This is now, is this expression unique? We will have to show the direct sum, na? So we will have to show that this equation is unique. I mean this representation. So if alpha equals to this, okay, and alpha is in Wi, since alpha is in Wi, it's in the range of ei, so alpha is of the form alpha I beta I. So see, what is ej alpha? So ej alpha is nothing but ej of alpha 1 to alpha k, which is ej of alpha 1 up to ej of alpha k. But what are the alpha k's? That is ei beta I, right? So write ej e1 alpha 1 up to ej ek alpha k. But you see, they satisfy this, right? ei ej is 0, na? Thus, the only surviving term will be ej square alpha j, okay? Which is alpha j, because ej square is ej, okay? This shows that v is the direct sum of I, okay? Adapt to I. Oh, exercise is there. Let's try out a few. Let V be a finite dimensional vector space. W is a subspace of V. Prove that there is a subspace W2 of V such that. Can you try one? V is a finite dimensional subspace of V such that this dimension V is dimension W. Can you do this too? Can you do it? Please try it. 1 and 2. Try for a few minutes. let's do it. I think the first one is pretty easy. V be a finite dimensional vector space, W be any subspace of V. So consider a basis beta 1 of W1, extend beta 1 to a basis beta of V, define beta 2 to be beta minus beta 1, okay, and define W2 to be span beta 2, okay. Then you can see that V is span beta, that is span beta 1 union beta 2, that is span beta 1 direct sum span beta 2. Since beta 1 beta 2 are linearly independent, okay. What about this 2? So V is given to be the sum of this, okay. So but the direct sum is not yet there, okay. So define beta I to be a basis of Wi, okay. Clearly beta, that is union beta I mean I'm writing this way, beta 1 like the ordered basis, the way we write it, is a basis for V, right, as V is, as V, since V is summation Wi, that is summation span beta I, that is span beta 1 to beta k, right. This thing is clear, but dimension Wi is of course cardinality of beta I, that is true na, dimension Wi is cardinality of beta I. Okay, and what we will have to show? We will have to show that W1 direct sum this, right? So let's see which one will be easier to show. So there are a few equivalent criteria. See the converse part, okay? And tell me, can we show these things? Can we show 1, 2, 3? If we can show 1, 2, 3, then we know that V is the real sum of this. Okay, so what is the obvious way to define an EI? So let's see if there are any more criteria. So can we show these things? Can we show these things? I mean this 1, 2 and 3. If we define, say if we define for any vector V, there exists uh, alpha 1 to alpha k, alpha I belongs to Wi, right? As V is this, but is this representation unique? So suppose V is again beta 1, I mean not beta 1, so let's V1 to Vk. Can I say this representation is unique? Otherwise I won't be able to. Somebody is saying something. So how should we proceed? How should we proceed? Can we define? But to define EIV of alpha, I have to talk about the well-definedness. Okay, so let's see one thing. So claim WJ intersection W1 plus WJ minus 1 plus WJ plus 1 WK is 0. Why are we trying to show this? Because once we show this, we can say this. Yes, we are trying to show that these are independent. Okay. Yes, yes, yes. So let's try to show these are independent. Because if these are independent, we know that this happens, this W becomes this, But from our definition, V is equal to W, na? So it is enough to prove that they are independent, okay? But for the independency, okay, so let's see. So suppose alpha j belongs to this intersection. So alpha j is of the form alpha 1 up to alpha j minus 1 plus alpha j plus 1 up to alpha k, where each alpha I belongs to wi, which is span beta I. Oh, I'm stuck here. Just give me a minute, just a minute. It looks very obvious, but it looks very obvious to me. But how should I write this? I can find a solution, but what I think is that the proof will be lengthy, but that shouldn't be the case. I'm looking for a more crisp solution. Okay, so one thing we can do, yeah, let's do that. Suppose alpha j belongs to this. Since beta I, since beta j is any basis of Wj, without loss of generality, we take alpha j belongs to beta j. Then alpha j belongs to span beta 1 up to beta j minus 1, beta j plus 1 to beta k, right? So alpha j is linearly dependent on beta 1 to beta j minus 1, comma beta j plus 1 to beta k, right? So the set, yes, this we are done. Beta j, beta k is not linearly independent. So what I am trying to say is that span beta 1 to beta j to beta k is strictly greater than summation. I mean strictly greater, what should I say, span this, which is v, as we have shown, is strictly greater than dimension wi equals to cardinality of beta I, right? No, it should be strictly less than, no? Sorry, because there are other vectors, which is a contradiction. Be writing like this. Okay. So again, what about 3? Find a projection E which projects R2 onto the subspace spanned by 1 minus 1 along with this. I hope you remember the notation. So first let's recall the terminologies. Yes, this was the terminology, right? Mhm. Okay. So first, let's write V as R direct sum n. Okay. So let's write R2 as R direct sum n, right? Where R is spanned by what? Onto the subspace. R is spanned by this, and n is spanned by this. Okay. So first let, so I mean like x1 x2 is equal to say a into 1 comma minus 1 plus b into 1 comma minus 2. Thus you get a plus b equals to x1 and 2b minus a equals to x2, right? You solve this and get b equals to x1 plus x2 by 3 and a equals to 2x1 minus x2 by 3. Thus you get x1 comma x2 is equal to x1 plus x2 in by 3 to 1 comma 2 plus 2x1 minus x2 by 3 into 1 comma minus 1. Okay, so that is your projection, right? So e x1 x2 will be in this component. So okay, you can also explicitly write down the matrix here, I think, because you take it inside 2x1 minus x2 by 3 comma x2 minus 2x1 by 3. I think you can write down the explicit matrix here, I think, by some mental calculation. X1 minus x2. So the first row will be 2 by 3 minus 1 third, and the second row will be minus 2 by 3 comma 1 third. I think that's your E. I mean in the matrix form. Yes. Okay. What about this? If E1, E2 projection onto independent subspaces, E1 plus E2 is a projection. True or false? Try this for a few minutes. Try this for a few minutes.
দাদা,
Yes.
এই আগের এক্সাম্পলটা একটু দেখাবে, যেটা 3 নম্বরের যেটা করলে?
Example or exercise?
হ্যাঁ, ওই এক্সারসাইজটা। ঠিক আছে।
Hmm. Okay. See, it is not true. So I can give you a counter example. So we have to show what? We have to show e1 plus e2 square is e1 plus e2, right? That's what we have to show. But what is this side? e1 square plus e2 square plus e1 e2 plus e2 e1, right? e1 square is e1 and e2 square is e2, so we get e1 e2 equals to minus e2 e1. But there is no guarantee that this will be the case for every projection e1 and e2. Okay. So we are taking a counter example. So the counter example is like this. Suppose you take e1 is this and e2 is this. Notice that e1 square is e1 and e2 square is e2. Okay. What is e1 plus e2? Okay. What is e1 plus e2 square? It is 1 2 0 1. Okay. So this did not happen. What about this? If E is a projection and F is a polynomial, then Fe is this. What are the terms E and B in terms of the coefficient of? Again, try for 2 3 minutes. মা 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 অল্প একটু বাড়ান দিও। Okay, so let's do it. So suppose first of all we notice one thing, that if e square is e, then e to the power I is e for any I, sorry. Okay, so let fx equals to summation ai x to the power I from 0 to n. So what is fe? Fe is summation Okay, I was thinking about one thing. I might be unavailable for maybe 1 week. I have to take my father to Hyderabad for treatment on the first week of January, maybe. So, if you guys are okay, then we can take 4 extra classes to compensate for that week, each in 1 week for the next 4, 5, 6 weeks. Okay. So, suppose on each Monday or maybe on each Wednesday, I take one extra class, one for analysis, one for metric space, one for abstract, and one for linear. Then those 4 classes will be compensated. So let me know if that's okay. So as they have taken, this is what are the terms. So A is A naught and B is summation AI, in from 1 to what about this? What about 6? What about 6? So Since T is diagonalizable, there exists a basis beta of V, maybe T is from V to V, such that T with respect to that matrix is this 1 0 1, and then again the eigenvalues is 0. Okay, so what is this? I hope you understand this. Right, this is nothing but the same matrix. Okay, so T square is T. T is projection. Okay, so we will call it up for today, and in the next class we will finish this exercise and see invariant sets and decomposition. Start from 2.4. And let's see, it will probably take, okay, let's see how much we can complete. Okay, so that's it.